Hello, so today we're going to prove the analysis of variance identity. And this is something that occurs in a vast majority of statistics courses which talk about ANOVA. And it's really a way of partitioning up variation. Okay, so we're going to prove essentially this statement here, which is the analysis of variance identity. But what does this mean? Well, let's imagine we have run an experiment, okay? And in the experiment, we have compared different treatments. So, for example, we might compare different fertilizers, so 4 or 5 or 12 fertilizers. And for each of these fertilizers or treatments, we have done the same experiment n times, okay? And we write down the results in a table like this. So y11 here is the first response to the first treatment. y12 is the second response to the first treatment, and so on until we get the nth response to the first treatment. We then do the same thing for the second treatment. So we do the first response to the second treatment, the second response to the second, all the way up to the nth treatment. And then again, we do the same thing all the way up to the 8th treatment. Okay, so the total number of runs of the experiment we do, n, is the number of treatments times the number of runs for each treatment. Okay, so we can come up with various different quantities that in some way summarize this experiment. Okay, so one important thing that we're going to need to know is the notation. So let's introduce this, and y dot dot here just means we're going to add up all the treatments and each of the runs within the treatment. So this is just going to be the total of all the responses for our experiment. Okay, so here we go. We're just going to add up all those numbers, and that we're going to call y dot dot. The other thing we might want to do is add up everything for each treatment. So we're going to add up over just all the different runs for each treatment, the responses. Okay, so for example, y1 dot will be everything within this purple box here. Okay, y11 or yi1 plus yi2 plus yin. Okay, so this is our notation, and what we want to prove, because it will be useful in what we then go on to do, is we want to prove that the sum of squares of treatments, sorry, the total sum of squares is the sum of squares of treatments plus the error sum of squares. So this first quantity here is the total sum of squares. This next quantity here is the sum of squares of treatments. And some people will say this is the sum of squares between treatments because it explains what the difference is between treatments. And this last quantity here is the sum of squares of errors. And again, some people will call this the sum of squares of residuals or the sum of squares within treatments. Okay, but I think it's easier to refer to it as the sum of squares of treatments and the sum of squares of errors or residuals. Okay, so all we have to do with this proof is prove that this top one is equal to these two beneath it. And essentially when we set these things up like this, it just becomes an algebraic proof. So let's think about how we might do this. Okay, well, let's write down So let's write down what the sum of squares, the total sum of squares is. So we're just going to use this definition. Okay, so what are we doing here? We're taking each of these data points, so each of these yij's, and we are subtracting them from, or subtracting the y bar dot dot from them. What is this y bar dot dot? Well, y bar dot dot is just my total. So this is what I worked out earlier here, y dot dot divided by the total number of experiments we did, the total number of runs. And similarly, I could write down that the mean for each treatment is just the total for each treatment divided by the number of runs I do for that treatment. So that will come in handy come in handy later. So the total sum of squares is really each response taking away the global mean y bar dot dot and squaring it and adding it up. So I take away the global mean from this and square it. I take away the global mean from this and square it and add all those quantities up. So this is the sum from I equals 1 to A, the sum from j equals 1 to n of yij minus y dot dot bar all squared. And what I'm going to do is I'm going to take away the same thing and add it on. So I'm going to take away yi dot bar and I'm going to add yi dot bar on. Okay, so I've taken the same thing away and add it back on. So it must just be the same thing. And just to make it really obvious, I'm going to just separate these things out. Okay, so these are now in two different brackets, and that's going to become important. Okay, so I now have a bracket which consists of something plus d, so this is c plus d. Okay, and of course this is just high school maths, where we can write this as c squared plus d squared plus 2cd. Okay, so this total sum of squares is going to be the sum of I equals 1 to j of this first term squared plus the sum from I equals 1 to a and j equals 1 to n of yi dot minus y dot dot bar squared. So this is each of these terms squared on their own. And then I'm going to have to add 2 times the sum between I equals 1 to a and sum between j equals 1 to n of yij minus yi dot bar and then yi dot bar minus y dot dot bar. Okay, so hopefully you can now see how this proof is taking place. And if we look at this term here, this is exactly this sum of squares of errors. So we're getting there. This term here, well, what can we do about it? Okay, so this term here, if you look at it, the summand, the bit within the sum, does not contain a j. Okay, so we're adding it up over j, but we're just going to add the same thing up every time because it doesn't vary with j. So in other words, we've got n times sigma I equals 1 to a of y I dot minus y dot dot squared. Okay, so students often get confused about this, but this is the same as saying, well, the sum between I equals 1 to n of, I don't know, a k is just n a k. Okay, our index here on the a does not involve I. So we're going to add up ak n times, and we're going to get n ak. So what is this yi dot minus y dot dot squared? Sorry, I missed a bar there. Well, this is exactly what we defined as SSTreat. Okay, so we're almost home because we've shown that my SST is SSE plus SSTreat, which is exactly what I wanted to prove, but in a different order. And I've just got this bit left over. So I need to show this last bit is in fact 0. Okay, well, let's just examine this last bit. Once again, this second term does not contain j. Okay, so we've got a yi dot minus y dot dot, the means of those things, but it doesn't contain j. So I could rearrange this as 2, sum between I equals 1 and a, yi dot minus y dot dot, the means of those things, and then everything else which contains j still has to stay within the summand. So we've got a yi dot bar. Okay, and these terms aren't squared, these are just linear terms. Okay, so we've got something times the sum between j equals 1 to n of yij minus yi dot bar. Okay, so I'm just going to now look at this last term here. We could show that this is just the sum between j equals 1 and n of yij minus the sum between yi dot bar between j equals 1 to n. Okay. So once again, we can add up these yij's. Okay. And this sum here is what I've called yi dot. And what about this thing here? Well, again, this index does not contain a j. So this is n yi dot bar. Okay, but what is yi dot bar? Well, it's yi dot over n. So this is yi dot minus, well, n times yi dot over n is just yi dot. So this whole thing is 0. So in other words, this term here is 0, i.e. this term here is 0. So this whole term here disappears to 0. So I am left with my result. That SST equals SSE plus SS treatment. Okay, so my proof is complete.